Now in part 3, now that we know how we integrate sines and cosines and tangents, and by extension cosecants and cotangents, we want to take this to some applications. Just because we've left the geometry stuff behind, right, doesn't mean we can't keep talking about them. What do I mean? Volume. We're still talking about volume, right? Okay. We have this curve here. Okay, it's in blue. Let me go ahead and get that here. This is curve in blue. Okay, y equals tangent square x. Okay, bounded by y equals 0. So that's going to be this line here. Okay, x equals 0. This line here. And then x equals pi over 4. So I have these indexed at, I believe, at every pi over 12, I think it is. And I know that tangent of pi over 4 is 1, squared out is 1. And it's actually going to be, let's see here, this line here. Let's go ahead and color in like we used to do. This here. And we are rotating around the x-axis. All right, so there's our usual picture. Just to remind us, I'll go ahead and write down here. This is pi over 4. Okay. Well, I'm rotating around the x-axis, so now we ask ourselves, do we want to use disks or do we want to use shells? Well, here, okay, if it were me, I think I'd probably want to use disks, because if I want to use shells, remember I need to slice parallel, okay? Shells are parallel, okay? I would slice parallel to my axis of rotation, but that means I gotta get this in terms of x as a function of y, and oh no, the square root of arctan of y? Do I really want to integrate something like that? No. So instead, I'm gonna go ahead and slice orthogonal the x-axis here, okay? Orthogonal to the axis of rotation, perpendicular to the axis of rotation, okay? And I want to use disks. Now remember our formula for disks, right? It's just pi times the radius squared, and how do you get the radius here, okay? Well, remember, pi times, let's see, integral from a to b of r squared dx. Well, the radius here, it's just the length of that strip, right? And what did we say? Go back to the video. Top minus bottom, right? Well, it's just going to be tangent squared. Okay, let's go ahead and do this here. This is easy. So the integral that we need is the integral from 0 to pi over 4, right? Top is tangent squared. Write it out in full. Minus 0 for the bottom, squared x. Well, tangent squared minus 0 is just tangent squared, and be tangent to the 4th. Oh boy, but how do I do that? Well, we have some tricks up our sleeve. Let's go ahead and write this. I'm going to write this as 2 copies of tangent squared here. Tangent squared x times tangent squared x. X, and is there a way I can rewrite tangent so I can get like something, the way I can do it? What about with secant? Secants are helpful. Ah, well, take a look at what we got here, okay? What we'll do here is write this as, let's go ahead and restart it over here. So what I will do, is now I'll write this as pi times the integral from 0 to pi over 4. Secant squared minus 1 times secant squared minus 1. Is that helpful? Square x minus 1 squared. Well, I know how to integrate a secant squared, and I definitely know how to integrate, 1. But do I know how to integrate secant to the 4th? Well, figure that one out, right? Here, let's write it out. So we'll have secant to the fourth x minus 2 secant squared x plus 1 x. The last two terms are easy. But what about that first term of secant to the fourth? Use that tangent again, right? Secant to the fourth. We'll rewrite it, okay? Let's do some stuff here on the side here so you can see what I'm talking about. Secant to the fourth of x we'll rewrite as secant squared squared, and we'll rewrite that as tangent, 1 plus tangent squared, I'll write it this way, times secant squared x. Now you see that it's helpful? I get something that pops out. All right, when we do the rewrite here, and I kind of am running out of room here, okay? Let's see here. I guess I'll, okay. Pi times 0 to pi over 4. Okay, we have secant square x times 1 plus tangent square x minus 2 secant square x plus 1 dx. Okay, now we break this into three integrals. The last two are easy. Okay, let's tackle the last two kind of on their own for a second here. This is getting quite messy. So I'm going to shuffle some terms over. So I'm going to go ahead and do the last two terms first. Integrating 1 gives me x. Integrating secant square gives me tangent. So I have 2 tangent x. And now for the last part, I'm going to go ahead and skim over the details here. But for this last integral here, which I'll do in green here, okay, I want you all to do u equals, what do you think? U equals tangent of x. Okay. That du is secant square x dx. Okay, when you do that, that last term will become, well, let's see, we'll have a 1 plus u square. So that'll become a u plus u cubed over 3. Okay, so u, remember, was tangent. Tangent x plus tangent cubed over 3. Okay, doing this for the sake of space here. All right, you can definitely see, right? If I compress that integral in green there, we'll have a 1 plus u squared du if we set it as its own term. Well, integrating 1 gives me u. Integrating u squared gives me u cubed over 3. And then replacing back will give me everything that I need. You can double check, right, that those two terms, you take the derivative, give you what you need back. Okay, now we do the evaluation, and it turns out that basically everything at 0 will vanish because the tangent of 0 is 0. You can see it in the picture. All right, let's go ahead and clean this up, right? So we have a pi over 4 minus 2 times tangent of pi over 4. Well, actually, take a look here. We got something clever here, right? I have minus 2 tangent x plus a tangent x. That's minus 1 tangent x. Then I have a minus tangent of pi over 4 plus 1/3 tangent cubed of pi over 4. All right. And then, of course, when I plug in 0, well, x equals 0. That's a 0. Tangent of 0 is 0. Okay, a lot of the stuff zeroes out. Okay, when I combine all this, let's see. We have pi times pi over 4 minus, well, tangent of pi over 4 is 1. And then cubing that gives me another 1. So we have a 1/3 in that term. And oh boy, this is going to be fun. Pi squared over 4. Okay, multiply those first two terms together. And then, once I move my big head out of the way, okay, 1/3 minus 1 is a negative 2/3. Let a pi through. And that's your volume. Now, of course, integrating the secant to the fourth there was probably the harder thing, okay? But take notes, okay? All that we did here was just rewrite and use something nice here, okay? We were trying to use that 1 plus tangent squared equals secant squared identity, okay, to give us something nice here. Of course, from that, okay, if you watch part 2, secant squared minus 1 gives me tangent squared, okay? So the integral in green was the only part that I left out there, but that's achieved by doing that u substitution, okay? U equals tangent of x. All right, let's go on to this other one here. Slightly more tame question here. We have cosine x as one of our boundary curves. Then we have y equals 0. That's not there. Y equals 0 is here. X equals 0. And then as the other boundary curve, x equals pi over 2. Okay, that's this one right here. We'll write that here. That's pi over 2. And we're rotating around the line y equals 1. So let's go ahead and draw that in here. I want to rotate around that region, that line. But which region do I color in? Well, let's follow the boundary curve. Okay. Y equals cosine x, y equals 0, x equals 0, x equals pi over 2. Going to be this region here in the. Okay, and we're rotating around the line y equals 1. Okay, and now we have our usual question: disks or shells? Now, it turns out that the shells integral will require you to do integration by parts, okay? Because you got to do an arc cosine thing and, you know, similar kind of thing when you're integrating a polynomial against an arc cosine. But let's think simply, right? Draw a strip here. I want to use disks, okay? Think about top minus bottom once again, okay? Outside minus inside. Draw a representative disk here. Not doing a very good job of, okay? And remember, like I said, discs are washers, okay? So this is technically a washer if you want to be specific, but I'll just call it a disc, okay? We'll think outside square minus inside square. Well, what is the outside and what's the inside? Think about this, okay? We're going back to the top minus bottom principle. So I want to do pi times the integral from a to b of outside squared, big R squared minus little r squared. Well, what's the outside and what's the inside? Well, the outer radius here, okay, let's think about it here. The outer radius, let's do color here. This outer radius, okay, is always 1, but the inner radius is the distance between, say, I'm going to colors here. It's the distance between the axis of rotation and the curve itself, okay? So that's going to be the inside radius, the one in blue, and the outside radius is in gray. So what do we have for our integral here? Pi times the integral from, well, 0 to pi over 2. Okay, outside squared, well, that outer radius is always 1, okay? Minus inside squared, let's think top minus bottom, right? Okay. For the inside radius, well, the distance there, okay? 1 minus cosine x. Careful with the placement of your parentheses, right? So let's recap on how we constructed that, okay? The outside radius, all right? Well, I'm always going to have that big circle, okay, formed by the bottom, that the line y equals 0. That's always going to be my outer radius. The inside radius will change with the cosine, right? As that cosine dips down, the gap gets wider. So the inside gap should be 1 minus cosine of x. That's the inside radius, and then we... All right, well, nothing new here. We just expand. Okay, remember that we want to use the formula a minus b square. Okay, so I'll just go ahead and make ourselves a little note here. I won't write out the formula again. Okay, a minus b squared is what we need to use there. So we have 1 minus, and I'll write 1 minus 2 cosine x plus cosine square x. Right, do some canceling here. Well, 1 minus 1 is 0. Minus times minus is plus, so 2 cosine of x. Then minus, okay, think about the distributive property, minus cosine square x dx. Well, the first term is easy. That's just a cosine by itself. What about the second? What do we use? Huh? What did we use? Well, let's go back, okay? If we go back to some of the problems that we did, we look and see, huh, Now, where did that cosine squared get turned into? Oh, it turns into that 1 plus, right? Half the value, double the angle. Using this formula up here, okay? Right, the cosine square using this half angle formula. Remember, half the value, double the angle. So let's go ahead and write that in, okay? So we go ahead and let's go ahead and write this so I can, that's a funny looking 2 up there, I'm sorry. Okay, 2, we have 2 cosine of x minus 1 half of 1 plus cosine of 2x dx. Okay, and now we just have a bunch of easy stuff. Antiderivative of 2 cosine x, that's 2 sine of x. And I'll have a minus, well, we multiply through minus 1 half, integrate that, you get a minus 1 half x. Now I have a minus cosine 2x over 2, okay, do some u sub. Well, antiderivative of cosine is sine, but then I need to divide by 2, so I get a 4 there. Okay, evaluate between pi over 2 and 0. Well, hey, this is your lucky day, right? Sine of 0 is 0. Okay. Of course, 1 half times 0 is 0. What's sine of pi over 2? Well, think about your unit circle, right? Sine of pi over 2 is 1. Okay. So we have some facts here. Sine of 0 equal to 0. Sine of pi over 2 is equal to 1. And I'm going to need sine of 2 pi because I have a sine 2x there, right? So sine of pi, 2 times pi over 2, is 0. We would have 6 evaluations here. 4 of them dropped out to 0. Isn't that useful? When you do all that work, okay? When you do all that work, you'll have pi times, well, 2 times the sine of pi over 2, that's 1 times 2, minus half of pi over 2 is pi over 4, and then minus, do we need to write something there? No, because 2 times pi over 2 is pi, sine of pi is 0, and 0 divided by 4 is 0. And then when I plug in 0, I just get zeros. So what's my volume? 2 pi square minus, nope, it is 2 pi minus pi square over 4. Isn't that pretty? Isn't that nice? Wasn't that straightforward, right? An application, okay? Something that we've already done before. Okay, just be careful about the method you choose. Again, you can do either one of these with shells, but it's more straightforward to do these with disks, okay? The integrals work out a little nicer. So now, hopefully, that you see how we can integrate sines and cosines, secants and tangents, combinations thereof, right? You got to use some trig tricks, okay? So it's a very good idea to refresh yourself on those identities. And remember, make sure that you have your trig identities handy when you study, right? It makes it easier, okay, when you work out the problems in practice, okay? Instead of trying to memorize what you're trying to do. This is not a memorization game, okay? Now, with this in mind, okay, we're done with the family of trigonometric integrals for now. But in the next section, we're going to be integrating some sums and differences of squares inside square roots. And that actually transforms us back into precisely these integrals. I hope you're ready for some square root action. See you in the next one.